sorts of new classes of planets around other stars. We're seeing worlds that are probably made up entirely of water. Some worlds that are probably made up of carbon. Some that are super Earth-like planets, that are rocky, that are 5 or 6 times Earth mass. I don't think that we know enough at this point to really rule out Pluto scientifically as a planet. The controversy came about because of the action of the International Astronomical Union that met a few years ago, and they came up with a set of criteria that must be met for an object to be classified as a planet. And the criteria were something like this. An object must be in orbit around the sun. It must be large enough that it takes on a nearly round shape, which is met by many trans-Neptunian objects. And it must have cleared its orbit of other objects. Well, it turns out that Pluto's orbit intersects the orbit of Neptune. For that reason alone, Pluto was declassified as a planet. If you look at a projection of its orbit and Neptune's orbit, you'll see that Pluto's orbit does intersect the orbit of Neptune. So Pluto has not technically cleared its orbit of other objects. In fact, because of the resonances, they will never be the same place at the same time. So it's physically impossible for them to even clear each other out of their orbit. Furthermore, as we're learning about other planets around other stars, we're finding some bizarre situations. There's one situation where it appears, again, the error bar is a little bit large, it appears as if there are 2 gas giant planets in the same orbit in resonance. If we use the IAU definition, then these 2 gas giant planets are not planets. So the IAU criteria are incorrect at best and probably a little bit absurd as we start looking at other examples of planets. On the other hand, the question of what constitutes a planet is a very important question because it pertains to the physics that goes into how planets are formed and what determines their structure. I think the idea that a planet must be in orbit around a star is a very legitimate criteria. That it be nearly spherical, I think, is a legitimate criteria. But the criteria that it must have cleared its orbit a degree is so loose that it's not even a useful criteria. Because what kind of degree does it have to clear? A grain of dust, plasma, a few asteroids? It's not obvious how you would put a line of demarcation on what it should clear and what it shouldn't. So I think that we've got work to do. The IAU refused to take up the issue again for its controversy. On the other hand, I think it was a really useful controversy. It got all sorts of students interested in Pluto. Why is Pluto no longer in the Planet Club? Launched January 17th, 2006. All I can say is that that was a great moment. I started working on Pluto in 1980. We had our first international conference on Pluto in 1993. We expect around 75 people. We had 200 people show up in Flagstaff, Arizona. That was the first time, 1993, that we started talking about a mission to Pluto. I mean, seriously, scoping out what a mission would be like. In 2001, we proposed. I was a co-investigator with a group that proposed a mission to NASA. A competitor group proposed a very similar mission, so NASA suggested we combine the 2 missions. We did. We proposed, was accepted in 2003, we built, launched 2006. We're not there yet. We've got 3 more years to go. And this is a very fast spacecraft. This left Earth at a velocity of about 37,000 miles per hour. Right after the launch, we had a post-launch party. Been working on this 13 years, so you go and you have a party after you launch. Okay, and the party was in Orlando. And then I went, caught a flight from Orlando to Baltimore, came home. By the time I got home, the spacecraft had passed the orbit of the moon. 9 hours. That's how fast it's going. And right now, we are just beyond the orbit of Neptune. We're just now getting there. Now, it's not that we're not doing anything along underway. We had all kinds of science observations. We did a slingshot, a gravitational slingshot of Jupiter. Jupiter has a lot of gravity, as you can imagine. This is a picture to scale. The Earth, the great red spot that you know all about, the storm the size of the Earth. But as we were flying by Jupiter, we got really lucky and captured this volcano on Io. Now, Io is about 1,800 kilometers radius. That's a 300-mile-long volcano. So where are we now? Right now, we are about right there. We're just coming up with the orbit of Neptune, and we will encounter Pluto in July of 2015. These two instruments here swap at Pepsi or plasma experiments. This is a high-resolution imager. This is a high-resolution infrared spectrometer. This is an ultraviolet spectrometer, and this is a radio science experiment. My role is that I'm one of the team members for the radio science experiment, and I'm the co-deputy of the co-director of the atmospheres team. Now, this is a mission, took a long time to plan, launch in 2006, get to Pluto in 2015, and we even have plans to go at least 5 years beyond that. So one of the details of the plan is that we have to build into the team structure renewal. Like the person that was the lead of the atmospheres team when we launched is going to retire. And then I will be the team leader after that happens, soon after we get to Pluto. So it's a very long-term mission. It takes a long time, a lot of patience. About 9-8 months before our encounter, we're going to begin our long-range observations of Pluto. About 10 weeks before the encounter, we will have images better than anything that we can do with the Hubble Space Telescope. 4 weeks before, we will begin around-the-clock observations of Pluto and Charon. The closest encounter, Pluto and Charon, will occur a little over 2 hours apart. And then we will take about 4 weeks just to download the data from that encounter. There's going to be a period of a little bit less than 2 hours where things are going to be very intense. We have thousands of observations planned in that encounter. And we've been working for years on the details of that planning. It's called the Pluto Encounter Planning Team. And I'm on that team too. And we have, basically, it's like a computer program where you program in sequences of events that are going to occur as the spacecraft goes by Pluto. And you can imagine with a variety of different instruments that have different pointing requirements, different sensitivity requirements. We're going to be pointing, so we're going to be clicking, pointing, measuring, pointing, clicking, rolling. And this is going to be a very intense period of activity with thousands of events over a period of about 2 hours of closest encounter. We will fill up a solid-state storage device and then send that information back over a period after the encounter. Now, it's not going to take 9 months to get the entire, before we will see everything. It'll take about 9 months after the encounter before we can get all the information relayed back to Earth. But there'll be snippets of information that we will get soon after the encounter. Again, it's going to be one of these things you're going to have a lot of patience because the image is going to come back slowly. This is a close-up encounter. Here's Pluto and its moon. New Horizons will fly just inside of the orbit of Charon, about a 10,000 kilometer distance. It will fly into the shadow of Pluto, and it will fly into the shadow of Charon. That's built into the timeline. Because one of the things I want to do is do an occultation of the sun. I want to look at how sunlight dims as it goes behind Pluto and Charon. We want to look at how radio signals dim. We want to look at how starlight dims as we move by Pluto and Charon. Okay, so what do we hope to learn? Well, as you can imagine, we want to improve on our knowledge. This is a best image that we have now with adaptive optics, reconstructions, playing games, educated guesses. We will have images that are at least as good as what we have of Triton, probably much, much better. We already know that the spectroscopy is going to be interesting. Why did I say that? We have spectroscopy of Pluto and Charon now that shows that there is methane on the surface in addition to the nitrogen. In fact, we can even develop maps of the methane distribution. You remember when I started, I showed you a measure or a map of the albedo radiation Here's a picture of the methane distribution of Pluto. Why is methane distributed in regions that look somewhat circular? In fact, a lot of the methane is at high latitudes and low latitudes. Does that mean that Pluto has polar caps of methane? Does that indicate seasonal transport? You can speculate a lot about why the methane is not uniform over the surface. This is going to be one thing we're going to be looking at. We're also going to be looking for the complex hydrocarbons like we see on Triton. We expect them to be there. If there's nitrogen and methane in the atmosphere, there should be a whole slew of hydrocarbons and nitriles on the surface or in the atmosphere. Complex organics. And there are many reasons for this. One is just the fundamental chemistry of what happens if you have methane and nitrogen in the atmosphere that's exposed to ultraviolet radiation and cosmic radiation. We expect it to break up and produce a complex set of hydrocarbons. These should settle down onto the surface, and you should have a rich mix of organics on the surface of Pluto. And we already have some observations which suggest that there are complex organics on the surface of Pluto. Go back to Pluto's escaping atmosphere. We have now a set of different perspectives on the escape rate of the atmosphere from Pluto. And if the rate is equal at all, like we think that it is, there should be accretion of the atmosphere that's escaping Pluto onto Charon itself. We've never seen anything like that in the solar system. I mean, in our Earth, the atmosphere is held so tightly, it's just trickling off into space and maybe a few atoms get to the moon. This is going to be a situation where most of the atmosphere is flowing out into space, and you've got another body out there, a moon, that's setting in this extended atmosphere, and it's going to be accreting the gas that comes from Pluto, a much more fluffy accretion. It's going to be gentle. 40 degrees Kelvin is pretty cold. As it accretes onto Charon, it might heat up to 100 degrees Kelvin. And so you're talking about a modest increase in compression. But that's tiny compared to the kind of things we see with binary stars. But the idea is that one planet can lose its atmosphere and it can be accreted about another object. That's something that we may see analogs when we study exoplanets. There's a whole host of criteria that we have for what we want to study with New Horizons for the atmosphere. I think I'll skip over the details of that. I think you know that we want to know composition, density, temperature structures. There are going to be some interesting things that are going to come out of this. We know that there are going to be sequences where we will be able to take pictures of Charon rise over the backside of Pluto. We know the celestial mechanics well enough that we know what these images are going to look like in terms of the geometry. There's going to be some pretty spectacular images that are going to be coming back. And we can even use things like this to do science. Reflected light off of Charon penetrating the atmosphere of Pluto can give us spectral information on the makeup of the atmosphere of Pluto itself. It's going to be an interesting mix of observations. To search for Kuiper belt objects that will be along the trajectory after we pass Pluto. And we have a mission that will go until the plutonium energy runs out around 2021 or so. And at that point, we will not be able to broadcast information back. So we have a period of about 5 or 6 years where we can take observations of other Kuiper belt objects, other trans-Neptunian objects, if we can find them close enough. And also, we have been very cautious. We have a principal investigator who's very cautious with onboard resources like fuel. And he's been carefully hoarding the fuel that makes trajectory corrections. And so we still have quite a bit of flexibility in how we approach Pluto, the little bit of flexibility in the distance, and in particular, where we're going to go afterwards. So if we, over the next 2 years or 3 years, find a good target that just takes a little bit of tweaking of the orbit down, that will put us right by that object, say 2 years after Pluto, we could probably do it. And we're not going to have nearly as close a flyby, unless we're exceedingly lucky, as we do with Pluto and Charon. But yeah, that's going to be there. That's certainly something we've been thinking about for a